Okie dokie. So today I'm doing a presentation, a brief presentation in the introduction of perovskite solar cells. My name is Harrison Lampy. I am currently a chemistry graduate student from Portland State University. See if I can move the slides. All right, so what I want you to be able to take away from this presentation, I want you to know what a perovskite is, what it means, and have like a picture that comes to mind in your head. I also want you to have an understanding of methods of analysis, so DFT calculations, X-ray crystallography. So perhaps those words aren't like something you haven't heard of before, and you know that they apply to the research in perovskites. And then I want you to ideally at the very end have an ability to generate some conversation around the current research. So, if someone were to bring up solar cells, you have some cool stuff to drop about perovskites on it. All right, so we're going to start with what is a perovskite. So it's a crystal structure. It has three main parts. In the corner here you'll see they're labeled ABX, it's ABX3. So the A consists of this organic cation, B consists of this metal cation, which is most efficiently been made with lead, which is this PB right here. More recent research has included bismuth and something else as a means to replace that lead, as lead is kind of toxic and we don't want toxic solar cells. And then X is the halogen anion. This is usually iodide. You don't necessarily need to remember that, but it's on there. So it's described as a cubic lattice structure. So you'll see in the corner here, these four or 8 blue points make this cube. Inside it, you have your halogen anions, and then in the center, you have your metal cation. And then over on the other side, you'll see how they connect. So they connect via the halogen anion. And then in the center here, you'll have your organic cation. And in these centers, you're going to have your metal cation. So these structures connect to one another, and these come together. So this whole structure right here will form an entire layer that is used as the light absorbing layer in solar cell material. So perovskite solar cells, why do we like them? There's this very like intimidating looking picture of this film laid out here. So why we want to make perovskite solar cells. So you've heard of solar panels. And when I think solar panel, I think the solar cells made with silicon, which is this thick, unbending, brittle sheet of silicon used to absorb light. So the idea with this crystal film, so it's this crystal structure suspended in a film, it would be more flexible. So with more flexibility, you can put it in more places. It could be more accessible that way. So if you're able to just one day want a solar panel, you don't have to have this whole metal rig set up to put it up in. You can just slap it on somewhere and it'll work. At least in theory, that would be the ideal way for solar panels to work. You can just stick in places. And then there's this cost-effective aspect. So there's this idea that it'll be less energy going into making them, and they would be easier to make than other solar panel materials. This is to be teetered with. So silicon solar panels are kind of made in mass in this big industrial complex, whereas filament solar cells, perovskite solar cells, have a few more steps to them. But the idea is it takes less energy to make them in the end. So what you're getting in energy out of the solar cell doing its thing is more effective. Now, how do we analyze perovskite solar cells? So in my research, I have found that these are the 3 different forms of analysis that come up the most often, and to me make the most sense to apply to researching perovskite solar cells. So there's density functional theory calculations, DFT calculations. They're just called DFT calculations. You don't need to worry about density functional theory in memory. So it's an electronic structure calculation. And what they'll do is they'll do a DFT calculation on a structure that they're thinking about to make a prediction as to what the actual findings will be. So this is usually the energy efficiency or how well they think, oh, this one method will show, because then they can find some differences. So if they predict that it'll work this way, and they stick it in something and it's either more or less efficient, they can go back and analyze, okay, what medium did we suspend it in? What did we make the actual structure we think we did? Ideally, you have a structure that works better than the DFT calculations show you, and then you can just step back and figure out, okay, we just need to do that again to get it to work better. It can also confirm that, like, okay, you made the structure that you intended to do, because there's these predicted calculations and our actual calculations line up with that. And then there's X-ray crystallography. So this is how they identify the crystal structure. So it's a beam of X-rays and they diffract off of crystal in specific directions. And those specific directions tell them, researchers, what the crystal structure actually is. Another way to make sure that they, okay, this is what we made, what we intended to make, and what it actually is. Sometimes they go in with the intention to make something and the crystal structure forms a bit differently, or they'll find out, they're like, okay, this crystal structure formed and worked in some places, but is falling apart in others. And then there's also UV-vis spectroscopy. So this analyzes the absorbance of light, one of the, I would say, more important bits. Once you got the DFT calculations, and the X-ray crystallography shows you that, okay, we made the structure that we intended to make. Now you want to know, okay, well, is it effective? Does this crystal structure you made when suspended in film absorb an adequate amount of light? And as research goes on, we're just trying to get more and more absorbance of light, better and better efficiency. So this works by a beam of light shines through a sample where a detector picks up what light comes through on the other side. And this allows them to understand, okay, these are the colors that are being absorbed. The more color it absorbs, the better, because you want to get all of the absorbance possible. There is a little bit more in absorbance where, like, it's better to absorb red light. But for the purposes of this presentation, all you need to know, DFT calculations are used to predict and then compare to what you actually find. X-ray crystallography is used to identify crystal structures by looking at diffracted rays of X-ray. And those specific directions tell you the structure. And then UV-vis spectroscopy will analyze that absorbance of light and give you a, okay, this is how good the solar cell is. Now, what has been done so far? So I've talked about this altering of the crystal structure. So it's this idea of the metal cation, as I said before, lead works probably the best for a perovskite solar cell right now, but lead is bad. Lead is toxic. We've all heard about lead paint. Lead is bad. So we want to remove the lead, but we need a new metal cation, so that's where bismuth came into play. And with using bismuth in the crystal structure, it isn't a perfect swap out. So they need to they'll pair it with, like, silver and have an interchanging pattern of bismuth and silver where the metal cation would be. Or bismuth iodide is another one that's popular. I'm sort of playing around with the metal cations and the halogen anions that bond them, that bond the crystal structure together to improve strength and absorbance. Also, in a paper I read, there's a changing in medium. So this is where we were talking about the DFT calculations. So according to the DFT calculations in this one article, they expected to get, I believe, a lower absorbance than what they actually got. And they found it's because they performed one test that conformed to the DFT calculations in one solvent and performed another in a different solvent and got better results. So this was the electrolyte versus the organic solvent in this paper specifically. I believe the electrolyte ended up working better in getting it that absorbance. So that's also in part why we have these DFT calculations. So we can find little fun things like this, and then they report on them, and it's great. And then another one that I've recently found is changing treatments before making the solar cell plate. So you build this crystal structure, you have it, the idea of the filament will be suspended in. Now there's the actual plating of it. So there is this precursor treatment, which in this image down here, and if my mouse will show like a little, you get the plate, you get what you want on it. And this one shows the lead iodide perovskite. This is just a free image I found online, but you can pretty much just cross out that name and switch it out with other things. So typically there's a precursor drop. So you have your crystal structure. You have the precursor drop, which is for lead has been DMSO and DMF. And then it goes into this spin coating where it spins on this to evenly spread everything out. And then there's this anti-solvent treatment. Then it sits for nucleation, and then annealing is just applying heat to making sure everything sticks to the plate. So you can't spin it and spin off, any more of the stuff you put on it. So what they found in changing the treatments is for lead iodide, there's this DMSO and DMF combination that works as the precursor. But for bismuth perovskites, and you'll see how all these things kind of blend together. It's not just going in one direction to make a better crystal structure. They found that DMSO and GBL, which is just a different liquid, those in combination for a precursor dropping actually improved solar cell performance, as well as adjusting this anti-solvent treatment for the bismuth as well. So the idea is that these are the three things that I have found that I find the most interesting. And I think these are some of the three more probable directions the research is going to be going. As far as, okay, we're always going to be altering crystal structure. That's kind of the standard. Changing mediums was found, I believe, 2019. Pretty cool to be considered for future use. And then changing the treatments before making the solar cell plate kind of comes after, okay, we have this crystal structure, it performs this well. Okay, we found these mediums, it performs this well. And then ultimately the treatments, and you'll find, okay, in the end, this is like the final product, and it performs as best as possible based on altering all these things. Now, some researchers not all papers consider all three of these. Usually it's altering the crystal structure and, one variable at a time, or these were all different papers focusing on different things. Lots of people altering crystal structure. I personally like the idea of changing treatments before making solar cell plates. I think it's pretty cool. And then here are my references. So if you want to read up about any of this on your own, go for it. Some of these, like LibreText chemistry, awesome. Totally recommend LibreText. Really, really nice. Other of these, like Introduction to Density Functional Theory, you can go for, but then the rest of these are more like this one by Jana, are actual research papers that I wouldn't expect my target audience to be reading, but go for it. We love reading this household. All right, I don't have a final slide. It's just my references slide. So I'm going to call it here. I'm going to post this to YouTube, and this is my project. Thank you.